This is my first of my videos in my module on the dot product of vectors. Okay, up until now I've discussed vector addition as well as vector or scalar multiplication with vectors, but not yet the dot product. So we're going to go ahead and start by defining it. We say the dot product of two vectors u and v, first of all, is written this way. So we say u dot v is how you would read this. U dot v is just basically how you would pronounce this here. So we have vector u dot v, but basically u dot v, we use this little multiplication dot here, and you can look at it as kind of multiplication, but it equals u1 v1 plus u2 v2, where let's just go ahead and point a few things out here. We say the vector u is in component form u1 comma u2, so u1 is the x component of this vector. Basically we're saying take the x component of the first vector times the x component of the second vector, and you get this product right here. What we'll do is we'll add on the product of the y components of the two vectors. So we say the x components and the y components, you multiply them respectively, essentially, and then you just sum those together. So the art of finding a dot product is actually kind of a really easy thing to do. So let's go ahead and take a look at a few examples. Down here, I do want to draw all these vectors in component form first, and then find their dot products, because there is actually a relationship between their dot product and the way they line up with one another. So let's see, 3, 4 here. So we go right 3, up 4, 1, 2, 3, 4. So this would be our vector here. We could call this the vector u if we wanted to. And then 8, 3. So we say right 8, 3, 4, 5, 6, 7, 8, up 3 here. So we say we want to find the dot product of these two vectors. You know, sketching it, that's not part of the dot product, but I do want to see this here. We say all we'd have to do is say u dot v is 3 times 8 here, 24, and then we'll add on the sum of the y components, which is 12. So in this instance, we get 36. So just basically, we just write the dot product of these two vectors is 36. So now an important thing to point out here is this. A dot product is always a scalar. So always a scalar. What do we mean by a scalar when we talk about vectors? We mean a number that is not a vector. It's just a real number. Okay, so a scalar is a real number, and that's what you get when you have a dot product of two vectors. Okay, so moving on to the next one here. Maybe we go and find the dot product before we sketch them. So we say 4 times 5 here is 20 plus 4 times a negative 5 here, and we get 0 in this instance. So what must be true when we sketch this image in? So we say right 4, up 4, 1, 2, 3, 4. So here's one of our vectors. Dun, 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 dun. And then our other vector was right 5. Down 5, 1, 2, 3, 4, 5. And so there's actually a relationship between these two vectors. I don't know if you can see it. It'll apply to a future video, but basically how they relate to one another. Their dot product being 0 could have told us how these would be kind of stacked next to one another. And then last but not least, dot product of these two, we say 0 times 5 is 0, plus now 4 times negative 2 is negative 8, and so we get negative 8, okay? And so sketching these in very, very quickly, we say 0, 4 is this vector that's up 4, left and right none, so here's our vector here, and then we say also over 5, down 2, so over 5, 1, 2, down. We say, okay, how these line up with one another is actually related to the fact that we got a negative, I would say a negative 8. But anyways, so that being said, that's how you find the dot product of vectors. We're going to go ahead and talk about some properties of the dot product because we would like to do some vector operations, okay? And so just very, very quickly, we say u, v, and w are vectors in the plane. We're going to call c a scalar. Remember, c is a number then. But basically, all these properties here apply. So things like, you know, u dot v is the same as v dot u. In other words, dot products are commutative. Or, you know, the 0 vector, which has a component form of 0, comma 0. If you take that times a vector v, you know, one could consider this if I took it times, say, v1. v2, sorry for the handwriting here. If you did a dot product of these two, you can see that you get 0 plus 0. But yeah, you basically get 0, and it's a scalar. Notice this is not bold-faced. Also, there's a dot product of a vector u and the sum of two vectors. Keep in mind, if you're doing order of operations, you would have done v plus w in the parentheses first, and then you get some new vector. You'll take that vector and a dot product with this vector. So basically, you're doing the dot product of two vectors. You get a scalar, but that's the same thing over here as saying we could take the dot product of u and v plus the dot product of u and w, which is a scalar plus a scalar, still a scalar, but essentially you could distribute a dot product, a vector through a dot product, if you're distributing it through a sum or a difference. This is way cool. Dot product of a vector in itself equals the magnitude of the vector squared over the length squared. Okay, that'll be our next video here. And then last property, last but not least, basically if you had a scalar and you were taking a scalar times the dot product of two vectors, you could take that scalar times the first vector first, distribute it through the vector, and then do the dot product. Or you could take that scalar and multiply it by the, or distribute it through the second vector and then do the dot product. You can get the same thing anyways. So it's all up to you, whichever is most convenient. Okay, so speaking of that, let's go ahead and take a look at this example we'll be done with this video. But we say let these vectors u, v, and w exist, and you can see their component forms there. But we say find each of the following. And also I want to tell whether the answer is going to be a vector or scalar. So maybe even before we start, we'll label these as vector or scalar. But you'll notice here, we say first thing we'd probably do is u dot v. Now what I want to point out here is this u dot v. Remember, a dot product yields a scalar answer. So now we're going to have some scalar times v here, scalar times a vector. And what do you get when you take a scalar times a vector? Well, you basically distribute the scalar through the vector and you get a vector answer. So let's go ahead and use the properties of vectors up here. Basically, we could do the u dot v first, and then we'll take that times the vector w here. So we say u dot v, this is the same thing as u, which is 3 comma 4 in component form, dot the vector v, and then v is the negative 2 comma 6. And so we say finding the dot product of these two things, this would be equal to 3 times negative 2 plus now 4 times 6. Essentially, you know, multiply the x components, y components, add those together. So we get negative 6 plus 24. And so this gives us an 18. Okay, so 18 here, basically what we've done is we found this first part. So now what we've got is this expression that's 18w. Okay, so here's our vector w. And so basically we need to take 18 times the vector w, which is the vector 1, negative 1. And remember, when you scalar multiply, you can just distribute this through. And so we get the vector 18 comma negative 18. Very cool, okay. So basically, you know, there's some vector operations in action. Or maybe if we were to go over here to letter B. Letter B says, oh man, you know, this is his last property up here. It says the scalar, we could take 2 times the vector w first and then do a dot product with u. Or, you know, you could do the scalar last. It's entirely up to us. We'll go ahead and do this. We'll say u and a dot product with 2w. We'll go ahead and do the 2w first. Why not? So we get this u. Actually, let's go ahead and write this out here. We say u. So 3 comma 4. U and a dot product with 2 times and w. Now w is 1 comma negative 1. So all written out, this is basically our u and a dot product with 2 and w. So we're going to go ahead and start with the 2 here. So we get this 3 comma, ooh, ugly 3 comma 4. Always do that on the outside, in a dot product with now 2 comma negative 2. And so now it's just a dot product. You know, we say multiply the x and y components. We say 3 times 2 is 6. Plus now 4 times negative 2 is negative 8. And so we get negative 2. But if you look at this, and actually, geez, I can't believe we didn't do this before we started the second one here. On the first one here, we said we were supposed to get a vector for an answer. We did get a vector indeed. On the second one here, we could have told you off the bat we were going to get a scalar. And here's the reason why. You know, a scalar times a vector yields a vector. So once we did this 2 times w, we got a vector and a dot product with a vector. But what do we know about dot products? Well, a vector and a dot product with a vector yields a scalar. Okay, and so we did get a scalar answer. So very cool.